So welcome to system class. So in today's class, we will be talking about the four characteristics which were discussed earlier. That is the first characteristic, uh, one we call as a, mutual exclusion. Mutual exclusion. Second thing, hold and wait. Third was no preemption, and fourth one was circular waiting. So these are the four characteristics of the deadlocks. And when these four characteristics are taken up, so we do have this origin towards the deadlock. Now it is up how an operating system is going to handle a deadlock. So if these four characteristics are occur at a time, then only the deadlock is going to come into picture. Then only the deadlock is going to occur. Okay. Now, how will we see that our system will never enter into the deadlock? So this is one of the biggest challenge. One was deadlock prevention. Two was deadlock avoidance. So we illustrate one state towards a deadlock, and if it is in that state, we assume that deadlock is never going to happen. So how to prevent our system so that it will not enter into the deadlock state? So that is what we are going to call here as restraining the values. So the first characteristic what a deadlock prevention is going to take up will be the mutual exclusion. Will be the mutual exclusion. So as we were mentioning, when we are going to call it as mutual exclusion, we will see that at most one process, will be in critical section. What is critical section? It is going to have the shared resources. So on a shared resources, we can make a read operation, nor we can do a write operation. So if there are read operations, we can allow multiple rates. If there are write operations, they can allow only a single user. Here we can have users in multiple number, then a mutual exclusion is going to come up into the scenario. If it is going to allow only a single user, then a write operation is going to take place. Okay, now when to see that a single user or when to see that a multiple users are there? Yes, if it is a read operation, then it goes with a read-only memory and it must hold non-shareable resources. So if the resource is not going to be shared, of course, then it can be going with a write operation. If it is going to be with a read operation, then multiple users can come into see at a time. At that case, read can happen. Okay. Now, coming back to the second characteristic of deadlock prevention. Coming back to the second characteristic of deadlock prevention, that is hold and wait. So, as per the definition of hold and wait, there is a process P1, and P1 is represented in circular box, in a rectangle box or a square box, and we do have some uh, so one second. So P1 is going to be represented in form of a in form of P1 will be represented in form of circle, whereas resources will be represented in form of rectangle, and every rectangle is going to have some instances. So I do have resource R1, and resource R1 is going to be used by P1. Here we are going to call that state as hold state, and it is going to ask for a resource to which it is in by P2 state. So this case we are going to call it as wait state, and R1 to P1 we are going to call it as hold state. So now how to see that we can prevent, how to see that we can prevent deadlock? Very simple. We must guarantee that whether a process requests a resource, it does not hold any resource. That means you have to break this chain. You have to break this chain. That means if P1 is going to ask for R2, then P1 has to release R1. Very simple. If P1 is going to, if P1 needs R2, then P1 must release R1. So this is the definition how a prevention is going to be acted over one of a deadlock characteristic. So in mutual exclusion, in a critical section, we have multiple shareable objects. And if there are shareable objects, if it is a write operation, we must see that only one process goes. But if it is a read operation, we can allow multiple operations. So if it is non-shareable item, when it becomes a non-shareable item, it becomes a write operation, then only it is going to be a non-shareable item. So if it is doing a write operation, it becomes a non-shareable item. So at most one process can hand over it. But if it is a shareable item, when it is going to be shareable item, when there is a read operation, then it is going to become a shareable item. So for shareable items, we can create multiple ways. For non-shareable items, that is for write operation, we can create only a single way. So I can write here. So for a read operation, we are going to call it as shareable. And for a write operation, we are going to call it as non-shareable items. Okay. The second prevention, how a deadlock will handle. The second one was hold and wait. So this scenario, it is going to bring up you. P1 is a process holding R1 resource, and it is going to request for a resource R2, which is held by P2. That means P1 is holding R1 and P1 is waiting for resource R2, which is held by a process P2. What is the solution? Break the chain. How to break the chain? If process P1 needs R2, then it must release R1. So if process P1 wants, or if it is waiting for R2, definitely it should release R1. In that case, the hold and wait chain is going to be taken up. Next one, how to see that no preemption will be handled. So how to see that no preemption will be handled? It is very simple that an algorithm to be converted from no preemption, it is very simple that the algorithm should be converted to preemption, should be converted to preemption. At that case, we are going to say that no preemption can be prevented. So we have preemption, we have no preemption algorithms. So we have already taken up shortest job first, FCFS, round robin, priority scheduling. So these are the different algorithms which we have provoked that they belongs to a preemption way, and shortest job first nor nor a priority scheduling, they can be migrated towards a preemption. They can be migrated to a word called as preemption rather than no preemption. So when we are going to say time interval t0, then I have p1, p2, and p3 are there. Time interval of 5, I am going to have p4 and p5. So these three are going to be executed. Later on, p4 and p5, they are going to be executed. This is taken up as batch 1, and the second one are going to be taken up at batch 2. So to break that chain, then the CPU is going to migrate its operations from no preemption towards a preemption operation. Then it is going to be successful. So the next one was, we are going, this is the no preemption. After the no preemption is going to take place, the fourth characteristic will be the circular waiting. So circular waiting, the scenario was, I have P1 process, then it is towards a P2, P2 towards a P3, and P3 towards a P4. So in between this, P1 is holding a resource R1, P2 is a resource R2, P3 is holding a resource R3, and P4 is holding a resource R4. But here I am going to have a hold and wait state, second state of hold and wait, third state of hold and wait, and fourth state of hold and wait. So we assume here there are multiple hold and waits which they are going to arise in form of a round robin fashion, in form of round robin approach. Now they are going to happen. So if we are going to break the chain, that is, instead of making a circular operation, if we see that there is no round robin operation in a scenario, then circular waiting is going to be blocked. So eliminate the round robin concept, that is, impose a total order resources, and they require that each process request is an increasing order of enumeration. So the order what we are going to decide, it should not enter into a cyclic. No cycle should not be formed, and it should be acyclic operation, and that acyclic order operation should be ordered, and it should be in a way that the resources are going to be processed one after the other. That is nothing but, if it can be a first come first serve order, then it may be one of a solution towards the circular waiting. So here is an example of a deadlock scenario. So we can see that there is a thread 1 and there is another operation called as thread 2. So here we do have a function. A function name is some do work 1, and it is going to implement some mutual exclusion. So this is sees that at most one process is taking up, and there is one more mutual exclusion. So we can see here, we call it as locking phase. These elements are called as locking phase, and here the do something, it is nothing but we have some critical section. And critical section, it is going to provide resources, and these resources are going to be shared. After the shared happens, now here unlocking is going to happen. So locking phase, we are going to call it as request phase, and unlocking phase, we are going to call it as releasing phase. So once you are going to enter into a critical section, later on we are going to move into the remainder section. So remainder section, we have non-shareable objects. We do have non-shareable objects. We do have some non-shareable objects. So at that case, we are going to say we are in a remainder section. Okay. Now there is one more function which it is going to take up. So this is a vice versa of the first operation towards the vice versa of the second operation. But the more or less this do something, that is the critical section what is illustrated. Similarly, the remainder section what it is going to be illustrated is going to be taken up. The only difference you can see, a mutual exclusion is having a vice versa operations between two or more processes. Okay, now how a solution is going to be provided. Okay, the first solution and the best solution will be the locking order. So how to give up a solution for that? So the solution for that, you are going to say it is locking order. So how does this locking is going to take place? One, we are going to call it as request for a lock, or we are going to call it as acquire. We do call it as acquire. Second, we are going to call it as using of a resource, using of a resource. And third thing, we are going to call it as releasing of a resource. So, or we are going to call it as request followed by acquire. Nor the second operation, we are going to call it as using of a resource. And the third operation, we are going to call it as releasing of a resource. So, request operation, we do call it as lock. Releasing operation, we are going to call it as unlock operation. Got it? So requesting the things towards an operation, we lock that shareable resources before we are going to use. After we are going to complete using of the shared resources, those resources will be given to the rest of a process. So how is they are going to be given to the rest of a process means they are going to say it as unlocking of operations. Now you can see there is a transaction. We can see that there are transactions, and this transaction is going to be concurrent. This transaction is going to be concurrent. Concurrent in sense they are going to be done in parallel. So one person sitting at one location using a Flipkart or an Amazon site buying the same product. Similarly, another person looking for the same product at her location and purchasing it at the same time. So two or more events are going to be using the same item at a time. Now, who should be given first? Who should be given next? So you need to give some set of ordering towards the concurrent process. So you need to give some set of ordering towards the concurrent process. Here is a banking example. So the banking example, you can see the transaction one, it is going to transfer some $25 from an account A to account B. So how it is going to be managed? So from account, that is, we call it as process P1. Next account, we are going to call it as P2, to which the data transfer is going to be migrated. And going to call it as an amount, and amount is nothing but the critical section, or we are going to call it as shared resources. Or we are going to call it as shared resources. Why we are going to call it as shared resource? Because P1 has to use the amount and P2 also use the amount. So for both of them, one he is going to put the $25 into an account, another he is going to consume the $25. So at this scenario, we need both the process. So for that, we are going to make a transaction. So to do this transaction, we want to see that at most one job at a time. To make at most one job at a time, it is going to be implemented with a word called as mutual exclusion. So mutual exclusion is done with two primitives, two primitive variables. First primitive variable, we are going to call it as lock1. Second primitive variable, we are going to call it as lock2. So acquiring of a lock. So you can see the get operation. We are going to call it as acquiring of lock. So lock1 is going to have a get lock, and from where this is going to be migrated. So we assume it as lock1 and lock2. So this is where you are going to see the scenario acquiring of the lock. Next one he is going to withdraw and another he is going to deposit. So at one transaction he is going to have a subtract operation, another operation he is going to make a addition operation. So after a lock has been made, then you can see this process as releasing of a lock. So this process, we call it as release. So acquiring of a process, requesting of a process. So acquiring of a process, we are going to call it as request. So using a shared variable, we are going to call it as use operation. Releasing of a shared variable through locking mechanism, that too with a mutex, that too with a mutual exclusion. then they are going to be done with a releasing operation. So now you can see the ordering. So which transaction is going to take up first, and which transaction is going to be taken up next. So ordering of between transaction 1, ordering between transaction 2 is going to be taken. So that is where a locking ordering happens. So first I need to do a withdrawal operation. Later on I'm going to do a deposit operation. So that sequencing mechanism is going to be decided by the operating system. So operating system, now it has assumed the concurrent processing, and for that concurrent processing it has given two operation. It has given from operation, then it has given a sequence operations between withdrawal and deposit. After performing a sequence operation with withdrawal and deposit, then it is going to make a release operation. So that is what how a concurrency control with the four basic primitives happen. So the four basic primitives, one we call it as mutual exclusion, second one we call it as hold and wait, third one we are going to call it as known preemption, and fourth one we are going to call it as circular waiting. So circular wait. So if these four come at a time, deadlock occur. So we are going to call them as characteristics. If we are going to eliminate, if we are going to eliminate the characteristics, then we are going to call it as deadlock prevention. So that is how you should understand the characteristics what were mentioned towards the deadlock or so that is regarding this shared content. So after this shared content has been used, the next primitive was the next one was we do have the continuation towards this topic. So we represent how to make an ordering, how to make a sequencing. So those we are going to discuss right now. So for that we are going to have this deadlock avoidance. We do have some deadlock avoidance in this scenario. So deadlock avoidance, after the four characteristics which were discussed, now we have this deadlock avoidance. So uh, so when coming to this deadlock here, so we do have some a priori information. We do have some a priori information. So a priori information is going to be an additional setup of this. So the a priori information is that number of instances, number of instances to a resource, number of instances to a resource is going to be taken up as an a priori information before we are going to handle up the deadlocks. So before we are going to handle up a deadlocks, a resource is there, and that resource is going to have some instances. So as a class, a number of instances are there. Similarly, for a resource also, we do have some resources. So for a process, how many number of resources we are going to give? So those number of items has to be allocated. Assume there is a resource, and resource is going to have 10 instances. Assume there is a resource and it is going to have some 10 instances. Now there are P1, there are process P2. Now process P1 is going to request for 5 resources. Process P2 is requesting for 3 resources. Now from this 10 instances, it is going to allot 5. From this 3 resources, it is going to allot 3, and it is left with 2 more resources. So that is how a banking mechanism towards a deadlock is going to be origined. So every process is going to have a process P1, process P2, P3, etc. And every process gets a request number of instances, and these number of instances, they are going to be allotted. So if I am going to ask for 5, 5 is allotted. If I am going to ask for 3, 3 is allotted. So in this way, a scenario is going to build up with banker's algorithm. a scenario is going to be built up with a banker's algorithm. So based upon the maximum need, how many number of instances a process needs towards the resource that it is going to be handled. So we are going to call here as a maximum number of resources for each type is going to be taken up. So we need to build a model, and that model is going to be built up with banker's algorithm. So we do have a deadlock avoidance algorithm, which it is going to be generated. It is going to be generated in a dynamically way. It examines the resource allocation state, and it ensures that it will never fall in a circular waiting condition. So process P1 to process P2, process P2, process P3. Now we do have a chain, and this chain has to be broken up. How is this chain eliminated? That is, how is this cyclic process converted to a acyclic process? That means there is no cycles. So to make that there is no cycles, then people are going to use this resource allocation state. They are going to use this resource allocation state. So via the resource allocation state only, the deadlock is going to be avoided. So a resource allocation state is a state which it is going to taken up acyclic order. That means it is going to build a tree order rather than a graph order. It is going to build a tree order rather than a graph order. So resource allocation state, now it is going to check up with the number of available items and the number of demanded items. So it is going to check up with number of available items towards the number of demanded items. I will just put a scenario here. I am going to have a resource R1, and R1 is going to have 10 instances. Now P1 is a process, P2 is going to be a process. Now it is going to say I demand. It is going to demand for 6 instances. This it is going to demand for 8 instances. Okay, it is going to put it in demanding for 6, and it is going to demand for 8. Overall 14 is the demand, and 10 we are going to call it as availability. Got it? So the resources is initially it is having 10 instances. P1 and P2, they are demanding for 14 instances, which it is not going to be rightly available with resource R1. So what it is going to do is, it is going to make a allotment. So you asked for 6, okay, now you go with 4. You asked for 8, okay, you go with 5. So in this way, it is going to give some order. It is going to give some allocation so that P1 and P2, they remain in safe state. P1 and P2, they remain in safe state. So to move that, the graph, it is going to be in a safe state. In a safe state, now there won't be any hang-up situation, so that the operating system can do its task very smoothly. At this juncture, it is going to take up with a smooth state, that too in a part of a banker's algorithm. So I am talking about one, we talked about availability. Next one, we talked about demanding. After availability and demanding, third thing we talked about allocation. So either an availability nor a demanding nor a allocation is going to be worked with a word called as safe state. So resource R1 is there, and R1 is going to have some 10 instances, and there are 3 processes, P1, P2, P3, and P3 is requesting for 8, P2 is requesting for 10, and P3 is requesting for 4. So 8 plus 4 plus 10, that is 22. But here I am going to have only 10. But still, I need to manage P1, P2, P3 with the availability with me. I should not disclose I am going to have only 10 instances. I can't manage. But still, P1, it is having only 10 instances. For that 10 instances, it has to give to P1, it has to give to P2, it has to give to P3, making an algorithm So that algorithm, it is going to build up with a word called as safe state, with a word called as safe state, and that it is going to be managed with banker's algorithm. So how is this banker's algorithm nurtured? The banker's algorithm is going to be nurtured with a primitives called as availability, with a primitives called as demand, and with a primitives called as allocation. So we do have these items. Now system, it is going to have a safe state, and this safe state, it is going to be mentioning with process P1, P2, P3, who is going to be allocated first, who is going to be allocated next, and ordering has to be taken up. We need to build an order, and that order we are going to call it as safe state. So ordering of a process P1, P2, P3, it is going to be mentioned, and that ordering we are going to call it as safe state. So here we can see that there is a set of sequence with all the processes. That is, a system is going to have some pi, pj, etc., and you should see that the availability of a resource, at the availability of a resource, and they are going to be held up, it should be always less than j. That means I am going to have 10, I am going to have I request for 8, I request for 10, I request for 4, it is going to have 10, still it is going to allot 2, 2, 2, maybe it is going to allot 3, 3, 3. In this way, the value which is given by the operating system will be definitely less than the demand what it is going to rise. Why it is going to be less than? Because it has to manage P2 and P3. P2, P3 doesn't know the request made by P1. Similarly, P3 doesn't know the request made by P1 and P2. Only the operating system knows what is the request of P2, P3, and P2. So based upon those requests and based upon the availability, it is going to allocate the resource. So for that, the value it sees that it always makes j as less than I. So we can see that a process pj, it need not be available, and it is going to wait for until pj is going to be waited. We are going to say a word called as mutual exclusion here. Next, pj is going to be finished, and pi is going to obtain the needed resources. So I assume that P3 has completed usage. So those 3 instances are now given to P2 or P1. So that ordering mechanism is going to be taken care with the operating system. So when pi is going to be terminated, so this is first condition. When pi is going to be terminated, it leaves all the resources which is going to be taken up. Assume P1 has completed his using of resource, whatever resources P1 has used, all those resources it is going to give back to the operating system. So the utmost condition or the basic facts why we are going to make a safe state, why we are going to make a safe state, because safe state will sees that there is no deadlock. If a system is going to be in a safe state, then we can see that there is no deadlock. When is no deadlock happened? 4 characteristics. One, we are going to call it as mutual exclusion. Second, we are going to call it as no preemption. Third, we call it as hold and wait. Fourth one, we are going to call it as circular waiting. If these are not going to happen simultaneously, then there is no deadlock. So how to manage there is a no deadlock? Yes, we have to give an ordering. How is this ordering given? The ordering is going to be given with a form of safe state. If there is an unsafe state, definitely it is going to lead up with a word towards a possibility towards deadlock. If we are going to see that there is a unsafe state, ordering is missed, circular waiting is going to happen, the resources are not going to be released, and it cannot be accommodated to another process, then again an unsafe state is going to be happen. So how to avoid it? We should ensure that the system will never be in an unsafe state, and we should assume that always a system is going to be in a safe state. If we are going to have a safe state, and if we are going to have a safe state sequence, then there is a possibility of no deadlock. No deadlock is going to happen. If there is no safe state sequence, then it leads to no deadlock, which is going to be very reliable. So in tomorrow's class, we will be taking up what is a safe state in detail and how it leads to unsafe state and what is a safe sequence, that we are going to take up with a detailed description with some example. Okay, so this is all for today. Thank you. Thank you for joining the class. Uh, so I'm downloading it. Uh, so stop recording.